It's project review time. So this is a new idea where basically, so I got to the point where I started to need, or kind of like, I'm really looking into actual projects, not just papers and algorithms, but I also want to take a look at real projects that people work on, quantum computing projects, of course. And and so, because I think that's super helpful for the person that is actually working or has worked on the project, but also for others to sort of get an overview on what's there. And then, if it's really just going to be a bird's eye view on the project, and then people can really dive into this by themselves. So I what I'm planning to do for today's video is probably a first one video, the first part, just taking a look at at one project sort of in general, and then diving into the code maybe a little bit. So this is going to be something new in the channel in terms of not just taking a look at circuits, but taking a look at actual code. And then maybe I'll do another video on where I'll try to actually run the project and validate sort of that that the stuff is working. So if you hear about interesting projects and you want me to review them, just let me know via the comments down below, or via Twitter, Facebook, or whatever you follow me, and I'll basically try to help you out, guys. Basically, taking a look at those projects. So. Of course, there is nothing better to do to start that series with the blog Masty Thoughts. That's a blog from Michał Stękłe. I hope I pronounce your name correctly, Michał. Part of my family is coming from Poland, czyli mogę trochę po polsku mówić. Just so that I can speak a little bit in Polish, but that's just the. And these are his projects. So I've been just really taking a look at it. And for some reason, I I like the yellow submarine one. It's together with Fali Bashige. Sorry for the names, and Przemek Chojecki. We've tried to solve the max-cut problem using continuous variable quantum computing paradigm with strawberry fields. So there's a bunch of new stuff for me in here as well. But there's code, research, and paper. So I thought that would be an interesting starting point. So let's get started with this. I'll just open the code, research, and paper. We're just in this first part of the video. We're just going to be really in explorative mode. So don't expect that I'll dive into stuff directly, but at least I want to get an overview on what's available there. So here we've got the repository. Pretty nice README file. Yellow submarine represented with a graph as a photonic quantum circuit. It's interesting. First time I hear about this. Then we use the strawberry fields engine to solve the max-cut problem. Okay, so I'll go back to this. Probably this is what we're going to focus on today. But there's basically a public research. Okay. Also, there's some actual experiments. What is public research? Bohr technology. What is Bohr technology? Develops quantum software and algorithms for solving complex optimization problems. Okay, so it's about optimization. And then there's public research. Okay. Interesting. There's definitely a lot of stuff to take a look at. So I hope this is going to be useful. Let me go back. Check reproducibility, right parameters, investigating layers. That's pretty. What is in there? Report. Correct report, all report. Never seen anyone before using GitHub to actually. It's pretty cool to actually do some public research. Overview. The main goal of this research was to check how similar are consecutive runs. Okay, so there's some research done, like sort of after running the program and then doing some kind of comparisons, reproducibility, correct version, code. Okay, interesting stuff. What else there is in here? Write parameters, investigating layers, report, figures, current report, yellow submarine finding parameters. So the code is, the main objective of the experiment was to find the right values of learning rate and regularization. Okay, so this is about, it's pretty cool. I like this because it's not just building something, but it's like there's stuff around it, like some research where then they use the algorithm, it seems like, to basically find the right values for the learning rate and stuff like that. Okay. Observation 1, with the regularization 0.1, values of most of the parameters went down to 0. With regularization 0.01, they were clearly diminishing over time. For smaller values, the effect was hard to notice. Interesting, you see. Okay, that's cool stuff. Everyone involved in this project, kudos. That's pretty cool. Investigating layers. Okay, I'll go through that. I'm even probably going to make 3 videos on this. That's pretty cool. Yellow Submarine report, investigation layers, current report. So, the main goal of this experiment was to investigate how the non-Gaussian layers influence the output. Interesting. The value of the cubic gate parameters changes during the training. Okay, I have no idea what a cubic gate is and what a care gate parameter is. Blah blah blah. Okay. This suggests cubic gate actually influences the output of the circuit, even if it doesn't boost the training. Okay. So there's a bunch of stuff in here. Then there's a bunch of stuff in. Okay, so then there's an actual paper, approaching graph problems with continuous variable quantum computing. Michał Stęchły, like Ntwali, Basig, Przemysław Chojecki. We introduced a method for solving the max-cap problem using a variational algorithm, and the quantum circuit consists of 2 parts. The first one, let me check the PDF. Okay, so that's an interesting. Okay, cool. June. So it's pretty recent. The paper is pretty recent. That's nice. And it's an introduction, related work, theoretical framework, Takagi decomposition, max-cut problem, circuit design. Okay, nice. Okay, that's pretty cool. So there's a lot of resources in there. So let me maybe take a look at so this is just the first overview. Let me take a look at the conclusions. That's pretty cool. Should be doable to go through those things in like a couple more videos. So what I want to do is I want to do a quick check on this, maybe the actual README file for the project, and take a look at some of the code, and then we'll do another video where I take a look at the actual the actual paper behind that, and then maybe the related research. That's pretty cool stuff. So Yellow Submarine. This repository contains code for solving the max-cat problem using given a matrix that represents a graph. We embed the matrix into a quantum circuit, which we then use to find the maximum cat of the initial graph. I'll have to refresh what the maximum cat of a graph is, but maybe they explain that later. Okay, what does it mean to embed the matrix into a quantum circuit? That's interesting. The max-cut problem is the max-cut problem is a problem that's known to be NP-complete. This means that while we may not have an algorithm for solving it that runs in polynomial time, we can take advantage of new computing power to solve the problem for graphs of bigger sizes. In this repository, we encode the graph as a quantum. In this repository, we encode the graph as a quantum circuit. Using the Takagi decomposition, we then use a variational circuit to help solve the problem. So this seems to me, just out of what I know so far, that what they do is they actually encode the graph as a circuit. So they use sort of some so they use some classical mechanism to decompose a graph into a circuit using this technique, Takagi decomposition, whatever that is. And then they use a variational circuit approach to solve the problem. The concept here is the same that I visited in some of my AI videos, quantum AI videos, where I think some of the basically different variations of the circuit are tested. So you change some things here and there, and then you see what works better. The variational circuit parameters are optimized during training. Okay, the parameters in this case are optimized. So not maybe you're not changing the gates or whatever, but that like the parameters of the gates. there's a video that I did on sort of a generic quantum machine learning model, which basically is doing that. So you've got gates that are parameterized, and then basically you can change the parameters. We can research on using this repository, and then the outcome of the research has been published and can be found here. Okay. Here, instructions on how to run the simulation. Let's see how well documented this is. First of all, without running that, can I understand the code? That's my first question. I'm assuming it's in here. And okay, you've got the solver and you've got an example. So I'm assuming I can take a look at the solver first. Blah, blah, blah. Michał is the author, the importer, the import statements. I'm by no means an expert in any concrete programming language. I do have a computer science master's, so I am able to understand computer science concepts, etc. But I have not really, I'm not really an expert on any specific language. So I might not, I might miss some specifics of Python or whatever, because that looks like that's Python. So you've got a class maxcat solver. So the maxcat solver algorithm seeks to find the maximum number of edges on a graph that, when cut each exactly once, their total weight is closest to the total weight of the graph edges. The problem is known to be to find number of edges on a graph that, when cut each exactly once, their total weight is closest to the total weight of the graph edges. The problem is, I don't know if I understand the way this is described in here. The maxcat problem. Wikipedia. It's a cat whose size is at least the size of any other cat. The problem of finding a maximum cat is described as a max cat problem. The problem can be stated as follows: one wants a subset of S of the vertex set such that the number of edges between S and the complementary subset is as large as possible. Okay. One wants a subset S of the vertex set such that the number of edges between S and the complementary subset is as large as possible. Okay. So sort of, I'm yeah. I mean, the utility of it probably depends on, what type of problem you're trying to specify. But the idea is that you wanna select. I mean, they're defining it in two different ways. You want to select the set of vertices that, So the edges between, here is like an example. You have like the black vertices and the white vertices. So the number of edges between each of them is as large, between the two sets is as large as possible. Okay. This class allows embedding the graph as a quantum circuit and finding the maximum count of the embedded graph. For reference, you can also calculate all solutions classically. Using this class, initialize with solver. Using this class, initialize with solver, maxcat solver, Learning parameters, training parameters, matrices, gate structure. Okay, learner parameters is a dictionary holding parameters that pertains to optimization. Training is the steps to be taken by the optimizer and the cutoff dimensions of the result. Matrix is the list of the graph adjacency matrix and the interferometer matrix, whatever that is, but it's probably the input of the problem. Gate structure is a list that contains configuration options. Okay, so you can maybe configure what gates, because what this is doing is basically trying to embed that into, or turn that into a gate, into like a circuit. So probably this is kind of allowing you to define certain constraints on what types of gates are in the circuit and stuff like that. Okay, this is for logging. So call the solver train and evaluate, to train and evaluate, and then assess all solutions classically, to get all solutions classically. Okay, the learner parameters, you've got task, regularization, strength optimizer, whatever. And then the training parameters, steps, cutoff dimension, matrices, list of the matrices, gate structure. So list of lists where each such list contains configuration of a gate parameters. List of lists where each such list contains configuration of a gate parameters. An example of such list is sgate 0 constant, where we seek to configure the squeeze gate. So these are actually gate configurations. Squeeze gate, sgate. What is a squeeze gate? So you've got the initializing function, you've got the training and evaluation circuit, which we'll dive into the next video. We've got the assess all solutions classically. Okay, so that could be the interesting one, is we build the circuit. S gates and D gates and key gates. I'll have to probably do some digging into what those things mean actually. With n blah 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 for gates. So this seems like it's basically iterating over something, and then it's actually building it's building the circuit. Cool. So this builds a circuit, and then here you get the circuit output, and then the loss function is probably what you want to optimize. Calculate cost once per. It's pretty short, so I'm quite surprised. It's interesting. Train and evaluate. Training and evaluation. Adjust the parameters of the circuit so the output minimizes the value of the loss function. After training is complete, the cost value for the initial circuit parameter is evaluated. Can I then evaluate just adjust? So this is where probably the magic happens, right? So this is where the actual training happens. So you're getting the variable gate structure. So you're getting all the gates from your gate structure configuration. Circuit output, load initializer, session run, circuit output, cost value, total cost value. But where is the actual optimization happening? Max cut solver. Maybe that's just the solver, that's just the class. So if I then go into the example, this is how you use that probably. Of course. So if you kind of set up the example, you set up the matrix, okay. Then you set up the learning parameters, the training parameters. Structure of the layers used in the variational part of the circuit. Ooh. What is this? And then run the simulation. I'm not entirely sure, but it seems it's small enough that we can actually, I think the best way to do that is if I just go and try to run it myself. And it's probably the best way to understand how this works, and that's probably what I'm going to do in the next video. I want to get this to work and then understand kind of step by step what's happening. So pretty cool. Um, it's an optimization problem, then I guess, and it's but I there's a bunch of stuff that I want to learn because the S gate, D gate, K gate, maybe I'll get it running first, and then I'll probably take a look at the paper. Maybe they explain a bit more about those concepts here first. And I hope that this is useful for you people. And as I said, if there's any projects you want me to review and sort of break down and take a look at, just let me know in the comments down below.